what is the true measure of loneliness? Is it the aching silence that can fall between two people in a room, or is it the immeasurable cosmic silence that separates two worlds? For all of our history, we have lived with the second kind, a profound and existential solitude. You are part of a grand planetary chorus, a symphony of existence that has been playing for billions of years without a discernible audience. Consider the sound of our world. It is never truly quiet. It is the percussive roar of a waterfall carving its story into ancient stone. It is the collective hum of a sprawling metropolis, a testament to our relentless ambition. It is the intricate whispered language of the forest floor, a universe of communication happening just beneath our feet. Life is noise. Life is chaos. It is the frantic beat of a hummingbird's wings, the deep resonant call of a blue whale plumbing the ocean's cathedral depths, the simple revolutionary sound of a child's first laughter. This vibrant, cacophonous, beautiful anomaly we call Earth is a riot of biology set against the velvet black of infinity. We are a singular point of light and sound, a vessel teeming with stories, with music, with questions adrift, on an ocean of staggering, almost absolute quiet. For centuries we have strained our ears hoping to hear a reply, a faint echo of our own song from across the void. We built colossal dishes, metallic ears turned toward the heavens, listening with unimaginable patience for a single structured whisper that was not our own. We listened for a pattern in the static, a ghost of mathematics in the cosmic radiation, any sign that someone somewhere was also looking out from their island of life and wondering. We have shouted our own messages into the darkness, encoding our science, our art, our very DNA onto golden records and beaming them toward distant star clusters. These are our messages in a bottle cast into a celestial sea of unimaginable scale, carrying the hopeful salutation of a species that dares to dream it is not a cosmic accident. But the silence that has come back to us is deafening. It is a quiet so deep and so persistent that it has become its own kind of data, its own chilling answer. This great silence is perhaps the most profound mystery we have ever faced. It forces us to confront a vertigo-inducing possibility that this entire sprawling universe, with its 2 trillion galaxies and its septillion suns, might just be an empty stage, and we are the only actors. Is it any wonder then that we have never stopped searching? The quest to find another world like our own is not just a scientific pursuit, it is woven into the very fabric of our being. It is an ancient primal urge to find kinship, to know that the blueprint for life, for thought, for consciousness was not used only once. This dream haunted the imaginations of our earliest ancestors, who populated the night sky with gods and monsters projecting their own dramas onto the silent, glittering canvas above. It was the dangerous heresy that drove philosophers like Giordano Bruno to imagine a plurality of worlds, each with its own sun, each a potential cradle for its own life. He paid for that dream with his life a martyr to an idea that was simply too vast for his time. That idea, however, refused to die. It blossomed in the minds of astronomers who, with each new lens they ground, pushed the boundaries of our cosmic neighbourhood further and further away. It exploded into a universe of possibility in the pages of science fiction, where we built starships of the imagination and voyaged to alien shores, meeting civilizations both wondrous and terrifying. These stories were more than mere escapism. They were a rehearsal for a future we desperately wanted to be real. They were a collective refusal to accept that we are a fluke. But for all our dreaming, the search remained indirect, a matter of listening and hoping. That has now fundamentally changed. In our time, in this very generation, we have undergone a perceptual revolution as profound as the one Copernicus sparked centuries ago. We are no longer just listening for distant voices, we are now actively looking for the homes from which those voices might one day emerge. We have become cosmic cartographers charting the celestial shoreline of our galaxy. With magnificent new eyes, instruments of breathtaking precision, launched into the cold clarity of space, we are pulling back the curtain of distance. We are learning to see the invisible. We can now detect the almost imperceptible dimming of a star, the telltale sign of a planet passing in front of its face, a fleeting silhouette against a thermonuclear furnace trillions of miles away. We can measure the subtle gravitational wobble of a sun, a celestial dance partner, being gently tugged by the orbiting worlds we cannot see directly. Each new detection is a triumph of ingenuity, a testament to our species' relentless curiosity. And what we have found has shattered all expectations. We have discovered that planets are not the exception but the rule. They are everywhere. Our galaxy is teeming with them. We have found worlds of unimaginable extremity. Gas giants larger than Jupiter, orbiting so close to their parent stars they are being boiled away in real time, their atmospheres stripped into space like the tail of a comet. We have found super-Earths, massive terrestrial worlds of rock and iron locked in gravitational duels with their siblings. We have found planets that orbit not one but two or even three suns, their skies painted with a perpetual alien twilight. We have found rogue worlds cast out from their stellar families to wander the cold interstellar darkness alone for eternity. We have found planets made of diamond and planets where it might rain molten glass. A galactic zoo of worlds each more bizarre and fantastic than the last. But among this staggering diversity, we search for something far more elusive, far more precious, a reflection. We hunt for the subtle signs of a world that feels familiar. A planet of the right size, made of the right materials, and orbiting its star at just the right distance. The so-called Goldilocks zone, that slender temperate band where liquid water, the essential solvent for life as we know it, could potentially pool on a rocky surface. This search has yielded dozens of promising candidates, worlds that tick many of the right boxes, igniting flickers of hope in control rooms and laboratories around the globe. But a recent discovery, announced not with the usual cautious optimism but with a palpable current of genuine astonishment, has sent a shockwave through the astronomical community. It is a discovery that moves beyond the abstract metrics of mass and orbital distance and touches upon something far more resonant, something elemental to the rhythm of our own lives. From a flood of data pouring back from the farthest reaches of our technological senses, a team of scientists, after months of painstaking verification and peer review, isolated the signal of a world designated K2 from 15b. It resides in the habitable zone of its star. It appears to be a rocky world, only slightly larger than our own. These facts alone would make it a remarkable find, another jewel in the crown of exoplanetary science. But it was another detail, a detail so specific and so profoundly terrestrial, that elevated this world from a point of interest to a global headline. As astronomers analysed the faint rhythmic fluctuations in the light bouncing off the planet's surface and atmosphere, they were able to calculate its rotational period. They measured the length of its day, and the number that emerged from their calculations was almost unbelievable. 24 hours, a 24-hour day. Let that sink in. Out of all the infinite possibilities, out of the chaotic dice roll of planetary formation, the universe has presented us with a world that spins on its axis in almost perfect synchronicity with our own. This is not just a number, it is a tempo, a heartbeat. The day-night cycle is the most fundamental rhythm of life on Earth. It is the metronome that has governed evolution for billions of years. It dictates when plants open their leaves to the sun, when predators hunt, when we ourselves are driven to sleep and to wake. It is the engine of our weather, the driver of ocean currents, the ancient clock that our biology is intrinsically deeply and irrevocably tuned to. To find another world that shares this specific pulse is uncanny. It feels less like a coincidence and more like a resonance, a harmonic echoing across the vast emptiness of space. It is a detail so evocative that it bypasses our scientific intellect and speaks directly to our imagination. It allows us for the first time to picture standing on the surface of another world and feeling a sense of temporal familiarity, of a rhythm that feels in some strange and profound way like home. This discovery changes the texture of the search. Suddenly we have a focal point, a specific named destination for our most audacious dreams. K2, 404b is no longer just a catalogue number, it is a place. But this revelation is not an answer. It is instead a much more powerful and tantalizing thing, a perfect question. The single shared characteristic of a 24-hour day is both a stunning clue and a potential cosmic misdirection. Does this shared rhythm truly make it a new Earth, a genuine sibling to our own world, Or is it merely a superficial similarity masking a world that is in reality profoundly and lethally alien? What does this discovery truly mean for the odds of life? How could such a familiar rotational period influence the development of a potential biosphere? Its climate, its geology, its very capacity to harbour the complex chemistry that leads to life. Finding this world is not the end of our journey. It is the dramatic opening of an entirely new chapter. We are now faced with the monumental challenge of moving beyond that single captivating data point and painting a complete portrait of this distant world. The path forward is fraught with immense technological hurdles and scientific uncertainty. The light from this planet began its journey to us long before we ever built the telescopes to catch it. To understand what is happening there now, we must push the very limits of our capabilities. We must find ways to dissect that faint ancient light, to search for the chemical fingerprints of an atmosphere, the telltale signatures of water, and maybe these subtle imbalances that could only be caused by biology. This documentary will take you on that journey. We will explore the groundbreaking science and the visionary technologies being deployed to bridge the chasm between our two worlds. We will join the brilliant minds wrestling with the profound implications of this discovery, and we will confront the immense challenges that still stand between us and knowing the truth. The question of whether we are alone in the universe has been asked for millennia. Now, for the first time in human history, we may finally have a place to look for the answer. Is our cosmic loneliness a fundamental truth or merely a temporary illusion born of distance? For nearly all of human history, this question belonged not to the scientist, but to the poet and the philosopher. It was a thought whispered in the firelight of ancient civilizations, an idea that flickered in the minds of those who dared to see the stars not as divine decorations, but as other suns. In ancient Greece, the philosopher Epicurus mused that to assume our world was the only one inhabited would be as absurd as assuming only one stalk of wheat could grow in a vast and fertile field. His was a universe teeming with possibility, a cosmos of infinite worlds born from the endless dance of atoms. Centuries later, the Italian friar Giordano Bruno would pay the ultimate price for this same vision. He imagined a magnificent, limitless creation, where every star was a sun, each with its own retinue of planets, its own Earths, each a potential home for life. For this cosmic heresy, for daring to shatter the comfortable confines of a single central world, he was burned at the stake. His persecutors could not accept a universe where humanity was not the singular focus of creation. His tragic fate serves as a stark reminder. The quest for other worlds has always been more than an astronomical exercise. It is a profound and often dangerous challenge to our sense of place in the universe. For millennia, however, these were just tantalizing thoughts, grand speculations trapped within the human mind. The sky was a beautiful but impenetrable barrier. The stars were unreachable, their true nature a complete mystery, and the idea of finding a planet circling one of them was a fantasy beyond the reach of any conceivable technology. Then a revolution arrived, delivered not through philosophy, but through two small, meticulously polished pieces of glass. When Galileo Galilei first pointed his primitive telescope towards the heavens in 1610, he did more than just magnify the moon and the planets. He shattered a worldview that had held humanity captive for 2,000 years. With his own eyes, he saw mountains and craters on the moon, proving it was not a perfect celestial orb, but a physical place, a world in its own right. He witnessed 4 tiny points of light circling Jupiter, a miniature solar system that demonstrated conclusively that not everything in the cosmos revolved around the Earth. This was the moment the floodgates of possibility began to creak open. The planets in our own solar system, once mystical, wandering lights in the night, were transformed into destinations. We saw the rusty ochre deserts and brilliant white polar caps of Mars, sparking a century of speculation about Martian canals and dying civilizations. We gazed upon the colossal, swirling storm systems of Jupiter and the ethereal, majestic rings of Saturn. These were not mere concepts anymore. They were worlds with weather geology and character. They were our cosmic neighbours. And yet the great abyss remained. Beyond the familiar shores of our own solar system, the stars remained stubbornly, defiantly as points of light. We knew now they were other suns, some smaller and cooler than our own others, blazing blue-white giants, but any planets they might host were impossibly small, impossibly dim, and impossibly far away. They were completely lost in the blinding glare of their parent stars, like trying to spot a firefly next to a searchlight from 100 miles away. A new kind of vision was needed, one far more subtle than simply looking. The hunt for exoplanets required us to learn how to see the invisible. The breakthrough came not from seeing a planet, but from seeing its ghost. Astronomers realized that while we could not detect a distant world directly, we could detect its subtle influence on the star it orbits. Imagine two dancers spinning together, one much larger than the other. Even if the smaller dancer is invisible, you can tell they are there by the way the larger dancer moves not around a fixed point, but in a small reciprocal circle. This is the essence of the radial velocity method. A planet's gravity tugs on its star, pulling it back and forth in a minuscule rhythmic dance. As the star wobbles toward us, its light is compressed, shifting slightly towards the blue end of the spectrum. As it wobbles away, its light is stretched, shifting toward the red. This tiny, almost imperceptible Doppler shift is the gravitational signature of an unseen world, a whisper across the void. At the same time, another group of pioneers pursued a different, even more intuitive method. They decided to wait for a planet to betray itself. If a planet's orbit happens to be perfectly aligned with our line of sight, it will periodically pass directly in front of its star. When it does, it will block a tiny fraction of the starlight, causing a brief, almost imperceptible dimming. This is the transit method. A cosmic shadow play a fleeting miniature eclipse that signals the presence of a world crossing the face of its sun. For decades, these methods were purely theoretical, pushing the limits of our technology. The signals were so faint, so buried in the noise, that finding one seemed a near impossible task. Then, in 1995, a discovery sent shockwaves through the scientific world. Swiss astronomers Michel Mayer and Didier Queloz announced they had found a planet orbiting the star 51 Pegasi. But this was no Earth. This world, the first confirmed exoplanet around a sun-like star, was a monster. It was a gas giant larger than Jupiter, yet it was racing around its star in a death-defying orbit of just 4 days. It was a hot Jupiter, a class of planet our theories said shouldn't even exist, roasted by its sun at temperatures hot enough to melt lead. It was bizarre, it was unexpected, and it was glorious. It proved once and for all that planets were out there. The hunt was on. What followed was nothing short of a scientific renaissance, an explosion of discovery that would forever change our cosmic map. The trickle of early detections became a flood driven by a new generation of incredibly sensitive instruments. And leading the charge was a revolutionary space observatory, a mission with a singular, audacious goal to find out if worlds like our own were common or rare in the galaxy. It was called Kepler. Launched in 2009, the Kepler Space Telescope was in essence a patient, unblinking eye. For 4 years it stared relentlessly at a single small patch of the sky in the constellation Cygnus, a region containing over 150,000 stars. It wasn't looking for wobbles, it was looking for winks. Kepler was a photometer of exquisite precision, designed to detect the minuscule dips in starlight caused by transiting planets. Its mission was a statistical survey on a breathtaking scale, a cosmic census designed to answer a fundamental question. The data that poured back to Earth was overwhelming, a torrent of light curves that teams of scientists and citizen volunteers scoured for the telltale signs of a passing world, and what they found transformed our understanding of the universe. The Kepler mission revealed not hundreds, but thousands of candidate planets. We found super-Earths, rocky worlds larger than our own. We found mini-Neptune's planets with thick, crushing atmospheres. We found planetary systems packed so tightly together, their years were shorter than our weeks. We found planets orbiting 2 suns like the fictional Tatooine. The sheer diversity was staggering. But the single most profound revelation from Kepler was a simple, powerful fact. Planets are not the exception. They are the rule. The data suggested that on average there is at least 1 planet for every star in the Milky Way. That is 100 billion stars and thus 100 billion worlds at a minimum in our galaxy alone. Suddenly the cosmos felt less empty. The whispers of Epicurus and Bruno were finally vindicated not by philosophy, but by overwhelming empirical evidence. Our galaxy was revealed to be a vast sprawling ecosystem of planetary systems. Following in Kepler's wake came its successor, the Transiting Exoplanet Survey Satellite, or TESS. Where Kepler performed a deep, narrow stare, TESS performs a sweeping all-sky survey. It is a cosmic cartographer systematically scanning the nearest and brightest stars in our solar neighbourhood. Its mission is not just to find planets, but to find the best and most promising planets for future study, the worlds close enough for us to scrutinise with our next generation of telescopes. Thanks to these missions, we have transitioned from an era of wondering if other worlds exist to an era of cataloguing them by the thousands. The question is no longer one of mere existence. The question now is far more focused, far more personal. In this vast ocean of worlds, is there another Earth? To begin answering that question, we first had to define what we were looking for. With a catalogue of thousands of bizarre and alien worlds, we needed a way to sift through the cosmic menagerie to filter for the planets that might be capable of harbouring life as we know it. The first and most famous criterion is location, location, location. Every star has what we call a habitable zone, a concept more popularly known as the Goldilocks zone. It is the temperate belt of orbits around a star where the energy received is just right, not too hot and not too cold for liquid water to potentially exist on a planet's surface. Venture too close to the star and any water boils away into a runaway greenhouse inferno like on Venus. Drift too far out and it freezes into a global ice shell like on Jupiter's moon Europa. This zone, this sliver of cosmic real estate became our primary hunting ground. The second critical filter is size and composition. We are looking for terrestrial or rocky worlds. A planet must be massive enough for its gravity to hold onto a substantial atmosphere, but not so massive that it becomes a gas giant like Jupiter or Neptune, a world with no solid surface to stand on. Our own Earth is the benchmark, a dense rocky sphere with a metallic core. Finding a planet of similar size and density orbiting within the habitable zone of its star became the holy grail of exoplanet astronomy. For years, these two parameters, the right distance and the right size, dominated our search for Earth's twin. And we found candidates. We found planets like Kepler 186f, an Earth-sized world on the outer edge of its star's habitable zone. We found worlds in the TRAPPIST-1 system, a remarkable collection of 7 rocky planets orbiting a tiny cool dwarf star. The census of potentially habitable worlds began to grow, yet a nagging and deeply complex third element was often missing from the equation, a factor that could make all the difference between a habitable paradise and a sterile wasteland. This crucial ingredient is one we experience every single moment of our lives, so fundamental that we often take it for granted, the simple act of planetary rotation. A planet's spin, the length of its day, is not merely a matter of celestial clockwork. It is a powerful engine that governs its potential for life in profound ways. Many of the rocky planets we have found orbit small, dim, red dwarf stars. Because these stars are so cool, a planet's habitable zone is nestled incredibly close, far closer than Mercury is to our Sun. This extreme proximity creates a powerful gravitational embrace, a phenomenon called tidal locking. Over eons, the star's gravity breaks the planet's rotation until it stops, leaving one side perpetually facing the star and the other perpetually facing the cold of space. The consequences are catastrophic for habitability. One hemisphere is trapped in an endless scorching day where the surface could be hot enough to melt rock. The other hemisphere is locked in an eternal frozen night, a crystal wasteland of solidified gases. Any atmosphere would likely collapse, freezing out on the dark side, while the sun-facing side is sterilized by unfiltered stellar radiation. A planet needs a day-night cycle. A reasonably paced rotation acts as a planetary thermostat, a global heat distribution system. It allows the atmosphere to circulate, carrying warmth from the day side to the night side, moderating the climate, and preventing the extreme temperatures that would make life impossible. Without this circulation, you do not have weather. You have a static, two-faced world of fire and ice. But the importance of rotation goes even deeper, creating something utterly vital for the survival of life on a planetary surface. It creates a shield. Here on Earth, our planet's spin, combined with its molten iron core, operates as a gigantic electrical generator. This is the geodynamo, and it produces a vast, powerful magnetic field that envelops our entire world. This magnetosphere is our invisible fortress. It extends tens of thousands of miles into space, deflecting the constant stream of charged particles from the sun, the solar wind that would otherwise strip away our atmosphere, and scour the surface with deadly radiation. A planet without a strong magnetic field is a world left naked and vulnerable to the fury of its own star. And the engine that powers this essential shield, this life-sustaining force field, is rapid rotation. For decades, this crucial parameter, the length of a day on a world light years away, was a ghost in the machine, a variable we could only guess at a number that remained tantalizingly beyond our reach. We could find a world of the right size in the right place, but we had no way of knowing if it was a dynamically rotating, climate-stable, magnetically shielded haven like Earth, or a tidally locked sterile husk. The puzzle of habitability was missing its most critical piece, until now. And so, the candidate was found, a whisper in the dark. Not with a sudden thunderous announcement, but as these things always begin with a flicker. A minute almost imperceptible dimming of a distant star, a loss of light so faint it amounted to less than 1/100th of 1%. It was an event so ephemeral, so delicate, that for millennia it had been utterly lost in the star's own boiling incandescent rage. But our eyes in the sky, the silent, patient sentinels we've placed in the void, see what we cannot. They stare unblinking for years on end, waiting for just such a cosmic secret to betray itself. This particular star, a quiet, unassuming dwarf star designated Kepler 186, had been under near constant surveillance. The torrent of data flowing back to Earth from the observatory was a river of numbers, a relentless stream of stellar photometry that required both sophisticated algorithms and the irreplaceable intuition of the human mind to decipher. For months, this single data point was just that, an anomaly, a ghost in the machine, a potential error in the instrumentation, a passing dust cloud, a statistical fluke. But then, precisely on schedule as predicted by the inviolable laws of orbital mechanics, it happened again. And again. And again. A rhythm began to emerge from the noise, a pattern, a pulse, a celestial metronome ticking off the passage of a world we had never seen. This was the transit method in its purest form, the oldest and most profound way of finding new worlds, a simple cosmic alignment of star, planet, and telescope. You are watching a shadow play staged across light years of empty space. The planet itself remains completely invisible, a speck of dust lost in the glare of its parent sun. All we can ever hope to see directly is its silhouette, and only then if we are lucky enough to be looking at the exact right moment from the exact right angle in the grand cosmic theatre. The persistent repeating dip in starlight was our first clue, the first thread in a tapestry we were only just beginning to weave. It was a discovery that sparked not celebration, but a quiet, intense focus. The hunt was on. Confirming the transit's planetary nature was the first monumental step, sifting it from a host of cosmic imposters. It could have been a binary star system where a smaller, dimmer star passes in front of its brighter companion, mimicking a planet's transit. Or it could have been interference from a background object, a faraway galaxy, whose light just happened to align with our target. Teams across the globe turned their own instruments toward that single, unassuming point of light in the constellation Cygnus. They cross-referenced star charts, analysed the star's light spectrum for any hint of a companion, and ran complex simulations to rule out every other possibility. It was a process of elimination, a meticulous, painstaking investigation, where every alternative explanation had to be systematically disproven. After months of this rigorous cosmic forensics, the verdict came in. The shadow was real, it was a planet, and from the precise amount of light it blocked during each transit, the depth of that dip in the data, we could calculate its size. The numbers that returned from the analysis were electrifying. The shadow belonged to a world just 10% larger than our own. Size alone is a tantalizing clue, but it can also be a cruel deception. A planet of Earth's dimensions could just as easily be a water world covered in a global ocean thousands of miles deep with a crushing high-pressure atmosphere, or a gas dwarf, a failed gas giant with a thick, suffocating envelope of hydrogen and helium. It could be anything. The location was the next critical piece of the puzzle. The time between each transit gave us its year, the duration of its journey around its star. This new world, which the team had provisionally named Ethelgard, completed one full orbit every 130 Earth days. Plugging this into our models of the star, a star smaller, cooler and dimmer than our own Sun, placed the planet's orbit squarely beautifully within the habitable zone. That temperate region, not too close and not too far, where the energy from the star is just right for liquid water to potentially exist on a planet's surface. It was the Goldilocks zone, that slender, precious sliver of celestial real estate, where the conditions for life as we know it might be met. We now had a world of the right size in the right place. The possibilities were staggering. Yet it was still just a shadow, a ghost defined only by its diameter and its orbit. To truly know Ethelgard, to see if it was a genuine rocky cousin to Earth or merely a gassy imposter, we needed to weigh it. And that is a fundamentally different and far more difficult challenge. You cannot place a planet on a scale across interstellar distances. Instead, you must watch its star. You must look for the wobble. Every planet, no matter how small, exerts a gravitational pull on its parent star. As Ethelgard orbits its sun, it doesn't just circle a static, immovable anchor. The two bodies are locked in a delicate gravitational waltz. The star, vastly more massive, leads the dance, but the little planet pulls back, causing the star to execute its own tiny counter-orbit. It sways, it wobbles it, inches back and forth, in a repeating pattern that mirrors the planet's year. From our vantage point, trillions of miles away, this motion is infinitesimal, a movement smaller than the width of a human hair seen from miles away. Detecting it requires an entirely different kind of observation. We turn to the world's most powerful ground-based observatory's instruments, equipped with spectrographs of breathtaking precision. A spectrograph acts like a cosmic prism, taking the star's single point of light and smearing it out into its constituent colours, a rainbow barcode of chemical information. Within this spectrum are dark lines, absorption lines, each one corresponding to a specific element in the star's atmosphere. These lines are the key. As the star wobbles toward us in its dance with Ethelgard, its light waves are compressed, shifting ever so slightly toward the blue end of the spectrum. As it wobbles away, the light waves are stretched, shifting toward the red. It's the cosmic equivalent of the Doppler effect, the same principle that changes the pitch of a passing ambulance siren. For months, astronomers charted this rhythmic blue shift and red shift. They were measuring the radial velocity of the star, listening for the gravitational whisper of its unseen companion. The data trickled in night after painstaking night. The signal was buried deep in the noise of the star's own activity. Starspots, flares, and convection currents on its surface all conspired to mask the planet's gentle tug. It took an international effort, combining observations from multiple telescopes to filter out the static and build a coherent signal. And then it emerged. A clear sinusoidal wave, the telltale signature of an orbiting body. The amplitude of that wave, the size of the wobble, told us the strength of the planet's pull, and from that we could finally calculate its mass. The moment of truth had arrived. The team ran the numbers, their hearts pounding with a mixture of hope and trepidation. Was Ethelgard a dense rocky world or a puffy, insubstantial ball of gas? The calculation was simple, but its implication was profound: divide mass by volume to get density. The result was a watershed moment in the entire history of exoplanetary science. Ethelgard's density was 5.6 grams per cubic centimetre, almost identical to Earth's 5.5. It was not a gas dwarf. It was not a water world. It was rock, iron, silicate, a terrestrial planet through and through, a true Earth-sized rocky world orbiting within the habitable zone of its star. In the landscape of exoplanet discovery, this was a monumental peak. We had found one of the most Earth-like planets ever discovered. But even this discovery, as profound as it was, carried with it a silent, ominous caveat. Most planets orbiting so closely to small dim dwarf stars are expected to be tidally locked. Just as our moon always shows the same face to Earth, these planets would be gravitationally forced into a state of synchronous rotation. One hemisphere would be trapped in perpetual scorching daylight, its surface a baked and desiccated wasteland. The other would be locked in an eternal frozen night, a cryosphere of unimaginable cold. Any atmosphere would likely freeze out on the night side or be stripped away by stellar winds on the day side. It would be a world of two extremes, a planet cut in half, with only a narrow twilight zone, the Terminator, offering any hope of temperate conditions. For all its promise, Ethelgard seemed destined to be just such a world, a fascinating but ultimately inhospitable oddity. This is where the story should have plateaued. Finding a rocky Earth-sized world in the habitable zone was already a monumental achievement. Determining its spin, its day-night cycle from such a distance, seemed like a challenge belonging to a future generation of telescopes, a task bordering on the impossible. How can you possibly measure the rotation of a featureless dot of light? You can't see continents, you can't see clouds, you can't see any surface features at all. The answer, it turned out, was not to look for features but to look for heat, to measure the planet's own faint thermal glow. As Ethelgard orbits its star, it goes through phases just like our moon. We see a full Ethelgard when it's on the far side of its star and a new Ethelgard when it's on the near side. While the reflected starlight is too faint to be of much use for a planet this small, the heat it radiates is not. Using the incredible sensitivity of our next-generation infrared space telescopes, we can measure the total light coming from the system, star and planet, combined with unprecedented precision. The technique is called phase curve mapping. The logic is as elegant as it is ingenious. As the planet orbits, we see different parts of its surface. If the planet has a day side and a night side, then as the hot sun-baked afternoon hemisphere rotates into our view, the total infrared light from the system should get a tiny bit brighter. As that hot spot rotates over the limb and the cooler morning side or the cold night side faces us, the light should dim again. The planet itself develops a thermal heartbeat, a rhythmic brightening and dimming of its own radiated heat over the course of its rotation. If the planet were tidally locked, this thermal peak would be static. The hottest point would always be directly facing the star, and the phase curve would be locked in sync with the planet's 130-day orbit. We would see one rise and fall of heat over the course of its entire year. But if the planet was rotating, if it had its own independent day-night cycle, the thermal heartbeat would be much faster. The hottest spot would be constantly moving across the planet's face, creating a rapid superimposed rhythm on top of the much slower orbital phase curve. The observation campaign was one of the most ambitious ever undertaken. For weeks, the space telescope stared at that one system, collecting photons one by one, building up a light curve of exquisite detail. The team knew what they were looking for: a second faster modulation hidden within the larger orbital signal. The initial data was awash in noise. The signal was so faint it was like trying to hear a pin drop in the middle of a thunderstorm. They developed new algorithms, new techniques for subtracting the star's own variability, for accounting, for instrumental drift, for teasing out a signal that was 1,000 times fainter than the noise surrounding it. Days turned into weeks. The team worked around the clock, processing, filtering, and reprocessing the data. They were searching for a pulse, a rhythm in the heat signature of a world they could never see. And then they found it. Buried deep within the data, a second frequency began to resolve. It wasn't random noise, it was a coherent repeating signal, a pulse, a distinct rhythmic rise and fall in the planet's thermal emissions. It was the planet's thermal heartbeat, and it was beating fast, unbelievably fast. The team worked feverishly to calculate the period of this new signal. They ran the analysis again and again, checking and rechecking, convinced there must be an error. The numbers simply couldn't be right. But no matter how many times they ran the simulation, no matter how they processed the data, the result was the same. The period of the thermal variation was not 130 days. It was not locked into a synchronous static stare. The data showed a clear, unambiguous rotational period of 24 hours and 17 minutes, a day. The discovery sent shockwaves through the entire scientific community. On a planet 40 light-years away, the sun rises and the sun sets. There is a morning, a noon, an evening, and a night. This single detail, this one number, was more transformative than anything that had come before. A rotating planet is a dynamic planet. A planet with a day-night cycle can distribute its star's heat, preventing the atmospheric collapse and runaway temperatures of a tidally locked world. This rotation would drive winds-power weather systems and create currents in any oceans that might exist. It creates a stable, globally moderated climate where temperatures are not locked into permanent life-extinguishing extremes. It transforms the planet from a static diorama of fire and ice into a dynamic, churning and potentially living world. Ethelgard was not just an Earth-sized rock in the right place. It had a rhythm, a cadence, a fundamental cycle that was shockingly profoundly familiar. It had a day just like our own. The shadow had been given substance. The ghost had been given weight. And now the silent, distant rock had been given a pulse. For the first time, when we looked up at that faint star in the night sky, we could truly imagine it. We could imagine a sunrise over alien landscapes, light catching the tops of mountains we've never seen, warming plains we've never walked. We could imagine the slow turn into dusk, the stars of a different sky emerging in the twilight. We had not just found a planet, we had found a world with a tempo we could recognize, a clockwork so uncannily similar to ours, it felt like a message sent across the void. The question was no longer just about its physical properties. The question had become deeper, more urgent, and infinitely more exciting. With an atmosphere, a rocky composition, and a day so much like our own, what else might this world share with Earth? What secrets could be hiding in its air, on its surface, beneath the light of its alien sun? And so, the signal was confirmed. The whisper from across the void, once a fragile hope held within a handful of encrypted data packets, was now a global headline. The tentative discovery we had followed through the long, quiet nights of observation suddenly erupted into a worldwide roar of confirmation. At press conferences from Pasadena to Darmstadt, the announcement was made, and with it a name was given to our phantom world, a name that carried the weight of a billion dreams, Elysium 4b. For a breathless moment, humanity stood united not by crisis or by conflict, but by a single point of light in the constellation of Lyra. It was a shared intake of breath, a collective pause in our terrestrial struggles to gaze outward at a possibility we had only ever dared to imagine. The data now open-sourced and flooding the servers of astronomical institutions everywhere became the most scrutinized artifact in human history. But as the initial incandescent wave of celebration began to subside, it was replaced by a more focused, more intense form of energy. The global scientific community, an organism built on skepticism and meticulous verification, began its sacred work. Every photon captured from Elysium S4's star system, every wobble in its radial velocity, every subtle dimming of its light was reanalyzed, stress-tested, and put on trial by the sharpest minds on the planet. This wasn't doubt, it was the highest form of respect. The claim was so extraordinary that it demanded an unprecedented level of proof. To truly believe in a new Earth, we first had to try with all our intellectual might to disprove its existence. We had to be certain that this wasn't an illusion, not a ghost in the machine or a misinterpretation of some bizarre stellar phenomenon. The search was no longer for a planet, but for the flaw. Yet with every new analysis, every independent verification, the conclusion held. Elysium 4b was real, and at the very heart of this burgeoning reality, at the core of this impossible discovery, was not its size, though it was uncannily Earth-like. It was not even its position within the star's life-giving habitable zone, that delicate cosmic shore where water could exist as a liquid. No, the truly revolutionary detail, the number that transformed this distant world from a promising candidate into a breathtaking parallel to our own, was the rhythm of its life, its day. The data was unequivocal. Elysium 4b completes one full rotation on its axis every 24 hours. This wasn't just a coincidence. It was a cosmic jackpot, a roll of the celestial dice that came up with a number so familiar it felt like a message. To understand why this single fact ignited such a firestorm of excitement, you have to understand the tyranny of the alternatives. For decades, our models of exoplanetary systems had been haunted by the spectre of tidal locking. This is the grim fate of planets orbiting too closely to their smaller, dimmer red dwarf stars. Gravity's relentless embrace slows their spin until they are captured one side, perpetually facing their sun, in an unending hellish day, the other locked in an eternal frozen night. On the sun-facing side, any oceans would boil away the very rock of the surface, potentially melting into a sea of magma. On the dark side, the atmosphere would freeze solid, snowing down onto a desolate landscape of nitrogen and carbon dioxide ice. A sliver of twilight, a so-called terminator zone, might exist between these extremes, a place of perpetual hurricane-force winds, as superheated air from the dayside violently collides with the cryogenic temperatures of the night. Life, if it could exist there at all, would be clinging to a knife's edge in a world of eternal screaming twilight. At the other end of the spectrum are the gas giants and failed stars in our own solar system. Consider Jupiter a world that spins with such ferocious speed that its day lasts less than 10 hours. This dizzying rotation stretches its clouds into the planet-girdling bands and zones we can see with backyard telescopes. It generates storms larger than our entire planet, powered by winds that howl at hundreds of miles per hour. Or look to Venus-Earth's so-called twin, a planet that betrayed our hopes. Its rotation is a funereal crawl, taking 243 Earth days to complete a single turn longer than its own year. This sluggish spin failed to generate a protective magnetic field, allowing the sun's solar wind to strip away its water. It also contributed to a runaway greenhouse effect, creating a stagnant, crushing atmosphere where surface temperatures can melt lead. These are the brutal realities of planetary physics. The rotation of a world is not a minor detail. It is the master clock, the central engine that drives its entire environmental system. It is the invisible hand that separates a dynamic living world from a static dead one. Elysium 4b, with its 24-hour day, has escaped these fates. It is a world in motion, a gravitational gyroscope spinning at a rate that is, for reasons we do not yet understand, the Goldilocks standard. This rotation is the planet's circulatory system. Imagine the sun's energy as a constant, powerful injection of heat. On a tidally locked world, that injection is a relentless blowtorch aimed at a single spot. On a rapidly spinning world, it's a chaotic, whipping spray. But with a 24-hour cycle, that energy is applied rhythmically, gently and evenly across the entire surface. The planet warms under the light of its star, and then crucially it has time to cool as it turns into the darkness of its own shadow. This constant, gentle cycling prevents the build-up of thermal extremes. It's the difference between holding your hand steady over a flame and rotating it evenly. One leads to a severe burn, the other to a pleasant warmth. This planetary convection, this simple act of turning, is the first and most critical ingredient for a stable global climate capable of supporting liquid water on its surface. This dynamic rotation does something else, something profound and beautiful. It stirs the atmosphere. As the surface of Elysium 4b heats and cools, it forces the air above it to move. Warm air from the sunlit equatorial regions rises, and cooler air from the poles, and the night side sinks to take its place. This is the birth of wind. But on a spinning planet, this simple movement becomes an intricate dance. An invisible force born from the planet's own momentum takes hold of these flowing rivers of air. We call it the Coriolis effect. It is the same force that dictates the spiral of a hurricane on Earth, that turns simple air currents into the vast, stable and predictable weather systems that define our climate zones. It organises the chaos. Without a robust spin, an atmosphere can become stagnant, or fall into simple, brutal patterns of pole to equator flow. With a spin like ours, you get complexity. You get jet streams, trade winds, and vast rotating pressure systems. You get the machinery of a working climate, and this is the moment where the story of Elysium 4b pivots. It transitions from a collection of astronomical data points into something our minds can almost touch. As the confirmation solidified, a new frantic race began, not in observatories but inside the humming water-cooled cores of the world's most powerful supercomputers. Climate modelers, the very scientists who predict our own planet's future, turned their vast digital engines toward this new world. It was a task of immense complexity, an act of creation in silico. They began with the precious few facts we possessed, the planet's mass and radius, which gave them its gravity, its distance from its star, which told them how much energy it received. And now the golden key, its 24-hour rotation period. These were the fundamental laws of physics for this new world. Into this digital crucible they poured assumptions based on our own cosmic neighbourhood. They seeded its virtual atmosphere with a plausible mix of nitrogen, oxygen and carbon dioxide. They gave it a hypothetical axial tilt similar to Earth's to create the potential for seasons, and then most audaciously of all, they gave it water. They programmed in the existence of vast oceans the amount inferred from models of planetary formation, and sculpted speculative continents, great land masses of digital rock. Then they pressed run. What happened next was a form of technological magic. For the first time, we were not just observing Elysium 4b, we were watching it come to life. Across thousands of processing cores, 1 billion years of simulated time could be compressed into a week. The models began to spin the virtual planet turning under its virtual sun. The initial output was a chaotic swirl of numbers and variables, but as the simulation stabilized, a world began to emerge from the digital noise. On screens in labs from Tokyo to Cambridge, the first weather maps of another Earth began to resolve. We could see thermal gradients form between the equator and the poles. We watched as the Coriolis effect took hold, twisting the developing wind patterns into familiar, elegant swirls. The first digital clouds began to coalesce over the warm, simulated oceans, gathering moisture and drifting on the newly formed currents. We were witnessing the birth of a climate. The fidelity of these models was astonishing. Scientists could see the emergence of great atmospheric convection loops, what we call Hadley cells, rising from the planet's tropics, carrying warmth and moisture toward its mid-latitudes before cooling and sinking again. They saw the polar vortexes, the vast cold cyclones swirling over the planet's poles, a direct consequence of its rapid rotation. They could model the theoretical jet streams rivers of high-altitude wind that would steer weather systems across the faces of its hypothetical continents. These weren't just abstract patterns. They were the very same atmospheric structures that govern life on Earth. They are the engines that pull moisture from our oceans and deliver it as rain to our farmlands. They are the systems that prevent our tropics from becoming uninhabitably hot, and our poles from plunging into a permanent deep freeze. And on the glowing screens of our most advanced computers, this same life-enabling machinery was self-assembling 63 light-years away. The simulations grew more and more detailed. Teams competed to refine their models, adding in the effects of atmospheric haze, the reflectivity of potential ice caps, and the thermal inertia of deep oceans. They began to produce breathtaking visualizations. We could fly through the skies of this simulated world. We could stand on a digital coastline and watch as a sun slightly warmer and more yellow than our own set over a vast alien ocean. We could track great swirling storm systems born in the warm tropical waters and spinning their way poleward, their structures uncannily similar to the hurricanes we know and fear. The colours on the climate maps told the most compelling story of all. Vast swathes of this world, entire continents' worth of digital land, consistently remained in the temperate zone, with average temperatures hovering between 0 and 30 degrees Celsius. The models didn't just suggest that liquid water could exist on Elysium 4b. They predicted that it would be stable, abundant, and globally distributed. They predicted oceans. They predicted rain. They predicted rivers and lakes and polar ice. This was a profound turning point in our perception. For all of human history, the idea of another world like ours was pure abstraction, a philosophical concept or a flight of science fiction fancy. We might have believed in the probability of it, but we could never truly feel it. Now we could see it. We could watch its weather patterns evolve in time-lapse. We could debate the likely climate of its western continents, or the severity of its polar winters. Elysium 4b was no longer just a name and a set of numbers. It had become a place, a destination for the human imagination. The dream of a second Genesis, once a faint and distant hope, was now being rendered in high definition, powered by terabytes of data and the collective intellect of our species. The models were, of course, still just that, models. They were intricate, sophisticated, and beautiful, but they were built on a framework of educated guesses. We had built a ghost, a spectacular digital projection based on the rhythm of a dance we could see, but the true nature of the dancer remained a mystery. The simulations provided a stunning, tantalizing blueprint for a habitable world, but they also cast into sharp relief everything we did not know. The simulations assumed an atmosphere. We had to prove one was there. They assumed oceans. We had to find the chemical signature of water vapor. They assumed continents. We had to search for ways to map its surface. Each answer these models gave us only spawned a dozen more urgent, more profound questions. And behind all of them, lurking in the space between the pixels of our simulations, was the ultimate question, the one that had driven our search from the very beginning. We had found a world with a rhythm so perfectly in tune with our own, a world with a climate engine capable of fostering life. We had simulated its winds and its rains. We had imagined its sunrises. Now we had to ask in this cradle, so perfectly prepared, had something awakened? Is there anyone home listening to the same steady 24-hour beat of their world and looking back in our direction? The journey to Elysium 4b was only just beginning. The echo of that perfect number, that impossibly familiar rhythm of 24 hours still rings in our minds. It was a moment of profound connection, a signal across the void that whispered a language we instinctively understood. For a breathless instant, the crushing emptiness of space seemed a little less empty, a little less alien. We had found a world that spins to our own terrestrial beat, a cosmic sibling turning in the dark. But the intoxicating music of that discovery, a symphony of hope played on a planetary scale, is now fading. In its place, a silence descends, filled not with emptiness, but with the weight of truly monumental questions. Euphoria, we are learning, is the easy part. The hard part, the work that defines our species, is what comes next. The truth is, a familiar day is just the first tantalizing line in a cosmic epic of unknown length and complexity. It is an invitation, not a destination. To truly grasp whether this world which we have named Ethel is a haven or a beautifully decorated tomb, we must move past the comforting cadence of its rotation. We must begin the arduous process of interrogation, peeling back its layers one by one. And the first layer, the very breath of a world, is its atmosphere. Without this gaseous envelope, this delicate membrane separating the surface from the hard vacuum of space liquid water, would boil away into nothingness. The perfect 24-hour day would be meaningless, merely illuminating a sterile, airless rock as it pirouettes through the void. So we point our instruments, our prosthetic eyes, 1,000 times more powerful than our own, back toward that single shimmering point of light. We wait for the precious moment when Ethel transits, when it slides in front of its parent star from our perspective. In that fleeting alignment, a sliver of starlight is forced to pass through the planet's atmosphere if one exists. This is our chance. That light becomes a messenger carrying an imprint, a chemical fingerprint of the air it has touched. The technique is called transit spectroscopy, and it is one of the most delicate and profound acts in all of science. We are in essence trying to read the ingredients of a world's soul by analysing the light that has grazed its outermost edge. The starlight arrives here on Earth infinitesimally changed. Certain wavelength specific colours in the spectrum will be missing, absorbed by the gases in Ethel's atmosphere. Each type of gas, oxygen, nitrogen, carbon dioxide, methane, water vapour, steals its own unique sliver of light. They are the phantom lines in the stellar rainbow, the silent testimony of a sky we cannot yet see. And so we hunt for these ghosts in the machine. We search for the telltale signature of nitrogen, the inert and stable bulk gas that makes up most of our own air. We look for the gentle dip that signals water vapour, the precursor to clouds and rain and oceans. We scrutinise the data for carbon dioxide, a greenhouse gas essential in moderation, a planetary fever in excess. But the signal we crave above all others, the one that would cause scientists to weep at their consoles, is oxygen. Oxygen is a violently reactive element. On its own, it does not want to remain free in an atmosphere for long. It eagerly binds with rocks and minerals on a planet's surface. On Earth, the vast reservoir of free oxygen in our air is not a geological accident. It is a biological testament, a constant exhalation of plant life and cyanobacteria for billions of years. Finding it in abundance on Ethel would be the closest thing we have to definitive proof of life. It would be the exhalation of a biosphere, a planetary lung breathing across the light years. Yet the challenge is almost beyond comprehension. The atmospheric layer we are trying to read is astonishingly thin compared to the planet itself. It is like trying to determine the exact composition of a peach's fuzz by viewing it from a mile away as it passes in front of a searchlight. The signal is minuscule, buried in cosmic noise, and the inherent flicker of the host star. Our greatest instrument, the James Webb Space Telescope, strains at the very limit of its capability to perform this miracle. every photon is precious. Each dataset represents years of planning and hope sifted through supercomputers to find a whisper of a hint. We might find a trace of water vapour, but is it enough to form oceans, or is it just a transient haze? We might detect carbon dioxide, but is it a sign of a balanced climate or a runaway greenhouse effect like Venus, a pressure cooker world hot enough to melt lead? Even a detection of oxygen comes with caveats. There may be non-biological or abiotic ways to produce it. Perhaps intense ultraviolet radiation from the star is splitting water molecules high in the atmosphere, creating a false positive, a chemical mirage of a living world. The data does not give us a clear photograph. It provides a cryptic riddle, a smudge of evidence we must interpret with painstaking care. But let us assume for a moment that we overcome these odds. Imagine we find an atmosphere that looks promising. Nitrogen-rich with hints of water and carbon dioxide, a composition eerily similar to a younger Earth. The next question on this cosmic checklist is even more fundamental: is there liquid water on the surface? The existence of an atmosphere provides the necessary pressure to keep water from instantly evaporating, but it does not guarantee its presence. For that, you need the right temperature. We know Ether orbits within its star's habitable zone, that so-called Goldilocks region, where it is not too hot and not too cold. But this zone is merely a guideline, a rough probability map drawn by astrophysicists. It does not account for the complexities of a planet's own climate system. A world with a thick insulating atmosphere might be a sweltering global jungle, while one with a thin atmosphere or highly reflective ice caps could be a frozen ball, a snowball planet locked in a permanent winter. We cannot see oceans directly. There is no telescope powerful enough to resolve continents and seas on a world so distant. Instead, we must again resort to deduction, to clever tricks of light. One potential method is to watch how the light reflected from the planet changes as it spins through its 24-hour day. If Ether has vast dark oceans and brighter, more reflective continents, its overall brightness would subtly fluctuate as different terrains rotate into view. The glint of sunlight off a planetary ocean, a phenomenon called specular reflection, could cause a momentary sharp increase in brightness. Finding such a glint would be an electrifying discovery, a shimmering confirmation of surface liquid. But it is a search for a flicker, within a flicker a momentary flash from a world that is already just a barely detectable pinprick of light. It is an observational Everest we are not yet equipped to climb with confidence. And even if we find an atmosphere and infer the presence of oceans, our investigation has only just reached the planet's surface. For a world to be truly and sustainably habitable, for it to foster life, not just for a fleeting moment but for geological eons, it must be alive on the inside. It needs a beating heart. It requires the slow, powerful churn of active geology. A geologically dead planet is a dead end for life. On Earth, plate tectonics are the planet's great recycling system. The crust is constantly being created at mid-ocean ridges and destroyed in subduction zones, dragging carbon and other essential nutrients down into the mantle and then releasing them again through volcanism. This process, the carbonate-silicate cycle, acts as a planetary thermostat, regulating carbon dioxide in the atmosphere over millions of years and keeping our climate relatively stable. Without this geological engine, a planet's climate can spin out of control, and crucial elements for life can become permanently locked away in the crust, unavailable to any budding biology. So how can we possibly know if Ether has volcanoes and shifting continents? Again, we turn to the atmosphere. A large volcanic eruption would spew sulfur dioxide and other telltale gases into the air, creating a temporary haze that we could potentially detect with our spectrometers. Finding such transient chemical signatures would be profound evidence of a dynamic churning interior. But the true importance of a planet's molten heart lies in the creation of something utterly vital yet completely invisible, a magnetic field. A planet's core, if it is partially molten and convective, and if the planet is rotating, acts as a colossal dynamo. It generates a magnetic shield, a magnetosphere that extends far out into space. This shield is our unsung guardian. It deflects the solar wind, a constant stream of charged particles pouring from our sun that would otherwise strip away our atmosphere over millions of years, boiling our oceans and scouring the surface with deadly radiation. Mars is a cautionary tale written across our solar system. It was once warmer and wetter with a thicker atmosphere, but its small core cooled and solidified early in its history. Its dynamo sputtered and died. Its magnetic shield vanished, and over billions of years the solar wind has been sandblasting Mars, leaving it the cold, tenuous, irradiated desert we see today. Ethel, with its promising 24-hour day, could be destined for the same fate if it lacks this invisible armour, and this brings us to the greatest source of both hope and peril in this entire story, the star that Ethel calls home. The nature of this celestial parent will ultimately dictate the fate of its child. Many of the most promising Earth-sized planets statistically are found orbiting red dwarf stars, also known as M-dwarfs. They are smaller, cooler, and far more common in the galaxy than Sun-like stars. If Ethel orbits such a star, the challenges for habitability multiply exponentially. To stay warm enough for liquid water, a planet must orbit a dim red dwarf incredibly closely, far closer than Mercury orbits our Sun. This proximity creates a host of problems. First, the gravitational pull at that distance is immense, constantly trying to lock the planet into a synchronous rotation, with one side perpetually facing the star and the other frozen in eternal darkness. Ethel's 24-hour day is a blessing, but is it a stable long-term state, or is it a temporary phase in a slow, inexorable march towards tidal locking? Is this perfect day we celebrate merely a fleeting moment in a billion-year-long twilight struggle against the star's gravity? The second and perhaps more terrifying problem is the star's temperament. Red dwarfs are notoriously volatile, especially in their youth. They are prone to frequent and violent stellar flares, tantrums of magnetism that unleash blasts of high-energy radiation and charged particles far more powerful than anything our Sun produces. For a planet orbiting in the close-in habitable zone, these flares would be catastrophic. A single, well-aimed blast could strip away a significant portion of a planet's atmosphere. It would bathe the surface in sterilizing radiation, a cosmic blowtorch that would be utterly lethal to any life attempting to gain a foothold. Even a world with a strong magnetic field might not be able to withstand such a relentless fusillade. Life on such a world would be a constant battle for survival against a sky that could turn traitor at any moment. It would need to be incredibly resilient, perhaps hiding in deep oceans or underground forever, shielded from the wrath of its own sun. This is the sobering reality that settles in after the initial celebration. Each question we answer only gives birth to a dozen more, each one harder and more profound than the last. And all of these investigations are shadowed by the immense, almost spiritual challenge of distance. Ethel is not a world we can visit or send a probe to, not with any technology we can currently conceive. Our entire understanding of this planet must be stitched together from the faintest of signals, from photons that have travelled for decades or centuries to reach our telescopes. We are attempting to write the biography of a world we can never touch based on a handful of scattered, whispered sentences. We are like detectives trying to reconstruct a complex crime scene from a single blurry photograph taken from orbit. Every conclusion is an inference. Every piece of evidence is circumstantial. The elegant rotation, the potential atmosphere, the inferred oceans, the hoped-for magnetic shield, they are all parts of a phantom world we are building in our computers and in our minds. The leap from this phantom to a confirmed living, breathing second Earth is a chasm wider than we have ever tried to cross. It will require new technologies, next-generation telescopes larger and more sensitive than anything we have today. It will demand decades of patient observation of gathering those precious photons, one by one, year after year, slowly building a case. The discovery of Ethel's 24-hour day was not the end of the search. It was the end of the beginning. It has proven that worlds like ours are out there waiting to be found. But it has also laid bare the staggering scale of the journey that still lies ahead, a journey not just across space, but into the very heart of what it means for a planet and for life itself to exist and to endure. The easy answers are all behind us now. From here on, the path leads only deeper into the great and beautiful unknown. And so we arrive at the precipice of the greatest question ever asked. For all our knowledge of Elysium 4b, its stately 24-hour spin, its gentle orbit within the life-giving warmth of its star, the elegant physics that govern its probable winds and tides, we remain cosmic outsiders, our faces pressed against an impenetrable window. We have found a world that feels uncannily like a memory of our own, a place whose very rhythm echoes the beat of our terrestrial hearts. But the final soul-altering inquiry hangs in the void unanswered. Is anyone home? Answering that question is not merely a matter of looking more closely. It is one of the most profound technological challenges we have ever conceived. The problem is one of light and of its tyrannical, overwhelming power. The star that gives Elysium 4b life also renders it invisible to our most intimate queries, drowning its faint reflected glow in a ferocious 1,000,000,000 deluge of photons. Imagine trying to spot a single firefly, hovering next to a colossal searchlight from a distance of 100 kilometers away. This is the scale of our predicament magnified to an interstellar stage. The faint chemical whispers from Elysium's atmosphere, the potential signatures of life, are utterly lost within the blinding scream of its parent sun. To hear that whisper, we must first find a way to silence the star. This is the task that consumes the dreams of a new generation of explorers, not astronauts in silver suits, but architects of light engineers and astrophysicists designing the next great eyes for humanity. They are sketching the blueprints for instruments so audacious, so ambitious, that they feel like artifacts teleported from a distant future. These are not just bigger telescopes. They are fundamentally new kinds of machines, conceived with a single spectacular purpose: to hunt for biology across the chasm of space. At the forefront of this vision is a concept that will one day dwarf all that has come before a successor to Hubble and the James Webb Space Telescope, currently envisioned under the name of the Habitable Worlds Observatory. Its mirror would be a vast segmented honeycomb of immaculate glass, 3 or 4 times the size of Webb's, a light-gathering titan capable of sipping the most delicate streams of ancient starlight. It would not be launched in a single neat package, but assembled in the vacuum by robotic artisans piece by painstaking piece, a cathedral of science constructed in the silence of deep space. Yet its colossal mirror is only half of the solution. Collecting the light is the easy part. The true genius lies in how this future observatory will surgically dissect it, performing an act of cosmic sleight of hand to make the star for a brief magical moment disappear. The most breathtaking of these concepts is known as a starshade. It is an idea born from the simple, elegant logic of a solar eclipse. To block the sun's glare, the moon passes in front of it. To block the glare of a distant star, we must build our own moon. Picture a colossal articulated structure shaped like a celestial flower, perhaps 50 meters across, unfurling in the void like a magnificent piece of origami. Its shape is no aesthetic choice. The petal-like edges are mathematically perfect, designed with exquisite precision to bend the waves of starlight around the spacecraft, preventing the star's light from diffracting and leaking around the edges to create a kind of false glare that would ruin the observation. This is not a blunt shield, but a finely tuned optical instrument in its own right, a masterwork of wave mechanics and material science. This cosmic sunflower would not be attached to the telescope. Instead, it would fly in perfect formation, with it separated by a gulf of space spanning 40, maybe 50,000 kilometers. 2 independent spacecraft, one the telescope, one the shade, maintaining their alignment across that immense distance with a precision measured in meters. Think of the challenge they must fly in a celestial lockstep so perfect that the shadow cast by this distant artificial moon falls precisely over the telescope's primary mirror, creating an almost perfect cone of darkness. From the observatory's vantage point, the star at the centre of the Elysium system would be perfectly eclipsed, its overwhelming light carefully and gently diverted. And in that manufactured twilight, in that tiny protected patch of engineered night, the faint jewel of Elysium 4b would finally emerge from hiding. The planet's light, a mere ghost carrying the secrets of its atmosphere, would journey across that vast gap, pass through the zone of shadow, and fall at last into the waiting embrace of the telescope. For the first time, we would see it not as a dip in a graph, not as a computed data point, but as a solitary, resolute speck of light, a world unto itself. But this grand interstellar ballet is not our only option. Another team of visionaries is working on a different kind of magic, one that happens not in the void between spacecraft, but deep inside the telescope itself. This method is called coronagraphy, named for the instruments used to observe our own sun's ethereal corona. It is an internal system of microscopic masks, mirrors, and optical traps, a labyrinth of human ingenuity built into the heart of the machine. As the torrent of light from the star and planet enters the telescope together, the coronagraph goes to work. It acts like a gravitational gyroscope for photons using a series of precisely machined occulting spots, some no wider than a human hair, to intercept the starlight at a focal point, blocking it directly. But that is not enough. The scattered and diffracted light still remains a hazy halo that would obscure the planet. So the next step is a miracle of adaptive optics. Deformable mirrors thinner than paper and vibrated by thousands of tiny actuators flex and ripple hundreds of times per second. They are controlled by algorithms of staggering complexity, which read the incoming waves of starlight and calculate their precise shape. The mirror then contorts itself into the exact opposite shape, generating a new set of light waves that are perfectly out of phase with the incoming starlight. When these two sets of waves meet the original starlight and its manufactured opposite, they cancel each other out in an act of near-perfect destructive interference. The star's glare is not just blocked, it is erased from existence within the machine. It is a process that demands a stability and quietness almost unimaginable, controlling vibrations at the atomic level to achieve a contrast ratio so extreme it borders on the unbelievable. Through this intricate internal dance of light and anti-light, the glare is suppressed by a factor of 10 billion, and what remains, what is allowed to pass through this gauntlet of optical traps, is the prize we have sought for centuries, the pure, untainted light of Elysium 4b. Whether by the grand shadow of a starshade or the intricate sorcery of a coronagraph, the goal is the same: to capture that fragile planetary light and feed it into the most advanced spectrometer ever built. This is the moment of truth, the climax of the entire endeavour, because it is within this light, within its spectrum of colours, that the chemical fingerprints of life might be hiding. When the light from Elysium 4b passes through its own atmosphere, the gases present their absorbed very specific frequencies of that light. When we on Earth receive that light and spread it into its constituent colours, a rainbow, we will see it is not a perfect continuous spectrum. There will be dark lines, missing slivers of colour, an intricate barcode that tells us with absolute certainty what that world's sky is made of. We are not just looking for any chemicals, we are looking for a very particular cocktail. First, we will hunt for the familiar signature of water vapour, the essential solvent for all life as we know it. Finding it would be a momentous discovery in itself, confirming the models of a temperate world with the potential for oceans and rain. But water alone is not a sign of life. It is merely a prerequisite. The true prize, the first of the great biosignatures, is oxygen. On Earth, our atmosphere is nearly 21% oxygen. We take it for granted with every breath we take, but from a chemical standpoint, this is bizarre. Oxygen is a ferociously reactive gas. It loves to bind with other elements. It rusts iron fuels fires and aggressively breaks down organic molecules. An atmosphere rich in free oxygen should not exist on its own. Over geological time, it would be scrubbed from the sky by chemical reactions with surface rocks and volcanic gases. A planet's air should not be filled with this chemical fire, unless something is constantly, tirelessly replenishing it. On our world, that something is life. It is the colossal planetary scale exhalation of trillions upon trillions of plants and microbes, performing photosynthesis for billions of years. Finding an abundance of oxygen in the atmosphere of Elysium 4b would be a profound and startling clue. It would suggest the presence of a powerful planetary-scale biological engine churning it out day after day. Yet even a sky full of oxygen could, through some exotic and unknown geological process, be a false positive, a clever imitation of biology. To build a truly unshakable case for life, we need to find its accomplice, methane. Methane is on the opposite end of the chemical spectrum from oxygen. It is a reducing gas, meaning it readily reacts as you with oxygen. In an oxygen-rich atmosphere, methane should be destroyed very quickly. It should have a fleeting ephemeral existence, vanishing in a puff of carbon dioxide and water. Finding both abundant oxygen and abundant methane in the same atmosphere at the same time is a stunning contradiction. It is like finding a lit candle and a puddle of gasoline coexisting peacefully in the same sealed room. It makes no chemical sense. The two gases are in a state of extreme chemical disequilibrium. They should have cancelled each other out long ago. Their continued simultaneous presence would be a nearly irrefutable sign that two powerful opposing processes are at work. One likely photosynthesis is pumping out vast quantities of oxygen, and the other likely the metabolic processes of anaerobic microbes is pumping out vast quantities of methane. This atmospheric imbalance, this perpetual chemical war, is what astrobiologists consider the smoking gun. It would be the closest we could get to proof of life without ever leaving our solar system, a chemical scream from a biosphere 50 light-years away. And this is where the unique nature of Elysium 4b becomes so critical. Its 24-hour rotation, the very feature that first captured our imaginations, plays a decisive role in this ultimate investigation. A tidally locked planet with one side in permanent day and the other in permanent night would have a far simpler, more static atmospheric chemistry. But Elysium 4b, with its dynamic day-night cycle, drives weather. It creates winds that dredge up gases from the surface. It creates pressure systems that mix the layers of the atmosphere. It likely forms clouds of water ice or other compounds, which could temporarily obscure the very biosignatures we seek to find. Our future observations would have to be timed perfectly, our models sophisticated enough to predict Elysium's weather patterns from light-years away. We would need to watch it for days, for weeks, observing how its atmospheric barcode changes as the planet spins on its axis, as different continents and oceans bathed in sunlight rotate into view. The planet's Earth-like spin transforms it from a simple static target into a living, breathing, evolving puzzle. Its dynamism makes the search harder, but it also makes the world itself a far more plausible and robust cradle for life in the first place. The very thing that complicates the observation is what makes the observation worth doing. So where does that leave us in this present moment, caught between a tantalizing target and the dream of future technology? The starshades and chronographs remain on the drawing boards. The great observatories of the 2040s are still decades away from their first light. We cannot today give you the definitive answer. The climax of this story is not a simple yes or no. The climax is something more profound, a newfound clarity of purpose. For generations, the search for extraterrestrial life has been a search in the dark. We have cast our nets wide, scanning thousands of star systems, hoping to find a world that was not too hot, not too cold, but just right. With Elysium 4b, that era is over. The painstaking analysis of its orbit, the intensive modelling of its climate, and the revolutionary confirmation of its stable Earth-like rotation have all converged to a single unambiguous conclusion. We have found our focal point. Of all the hundreds of billions of planets thought to exist in our galaxy, this one world, this spinning orb of possibility, has been elevated above all others. It is no longer just a candidate. It is the prime suspect. It represents the most compelling, most dynamically stable, most Earth-like case for a habitable world we have ever encountered. The vague galaxy-spanning search has now become a focused, targeted mission. The hunt now has a name and a location. The journey ahead is long, the technological mountains we must climb are high. But for the first time in human history, we know exactly where to point our instruments. We know where to aim our dreams. The question of life on Elysium 4b has now become the central unifying quest for a whole new era of exploration, a promise we are making to the future. A promise that one day we will silence its star and listen for the whisper of a biosphere. And so, we stand at the end of one journey and at the threshold of another. We began our story in the soft glow of campfires with ancient eyes turned upward. They looked to the same stars we see, but saw in them a celestial map of gods and monsters, of heroes and eternal questions whispered into the night. For millennia, the idea of other worlds was the domain of philosophers and poets, a dream of impossibly distant shores populated by beings of pure imagination. It was a question rooted not in data, but in a profound and deeply human loneliness, a yearning to know if this small blue spark of life was a singular miracle or a common flame. Then, slowly, painstakingly, we began to build our staircase to the stars. We learned to gather starlight not just with our eyes, but with lenses and mirrors, transforming those divine points of light into objects of scientific inquiry. We deciphered the language of light itself, learning to read the spectra that told us of a star's temperature, its age, its chemical composition. The universe, once a canvas for mythology, was becoming a physical place governed by laws. We could begin to comprehend laws that must apply everywhere. You've journeyed with us through that revolution in perspective. You saw the dawn of the exoplanet era, when the first worlds were revealed not as tranquil havens but as bizarre and violent infernos. These were the hot Jupiters, cosmic behemoths huddled so close to their parent stars that their years were measured in mere days, their atmospheres boiling away into space. They were magnificent discoveries, proof that planets were indeed common, but they were alien in the most fundamental sense, confounding our simple models of how solar systems were supposed to behave, how they were supposed to form. They taught us a crucial, humbling lesson to expect the unexpected. We refined our techniques, our gaze becoming ever more precise. We learned to watch for the most subtle of cosmic eclipses, the transit, where a planet's passage dims its star's light by a fraction of a percent. It was an astonishing feat of celestial photometry, like trying to spot a single firefly flitting across the face of a colossal searchlight hundreds of light years away. From these minuscule dips in brightness, we learned to measure a planet's size. By observing the gravitational wobble it induced in its star, we could measure its mass. Size and mass gave us density, and density gave us our first real clue as to whether we were looking at a ball of gas, a world of ice, or a sphere of solid rock. The search narrowed, zeroing in on the so-called habitable zone, that delicate orbital ribbon where temperatures are just right, not too hot, not too cold for liquid water to potentially grace a planet's surface. We found dozens, then hundreds of candidates in this privileged space. Rocky worlds of roughly Earth's size orbiting stars not unlike our own Sun. For a moment it seemed the galaxy might be teeming with Earth's twins. But a stubborn, inconvenient truth began to emerge from our calculations, a physical reality that seemed to place a cosmic lock on these promising worlds. Gravity. The relentless, patient and unforgiving force of gravity. For a planet nestled close enough to its star to feel its warmth, the star's gravitational pull is not uniform across its entire body. The near side is pulled more strongly than the far side, a differential force that stretches and flexes the planet, creating immense tidal friction. Over millions and billions of years, this celestial arm-wrestling match inevitably bleeds a planet of its rotational energy, its precious spin. One by one, our models predicted these worlds would become tidally locked forever, presenting one face to their star's light and one face to eternal darkness. One hemisphere a scorched desert, the other a frozen wasteland. The dream of an Earth-like world seemed to be perpetually trapped in this gravitational paradox, a cosmic catch-22. A planet needed to be close enough for warmth, but that very proximity seemed to guarantee a state hostile to the complex chemistry of life. The habitable zone we feared might be a celestial mirage. And then there was Elysium 4b, a single point of data, a whisper in the starlight from 480 light-years away. It was the right size, it was in the right orbit. It had all the hallmarks of another tidally locked borderline world. Our expectations, tempered by years of finding astrophysical oddities, were low. But the teams behind the spectropolarimetric high-contrast exoplanet research instrument, the pioneers of the incredible new science of rotational Doppler mapping, they kept watching. They kept listening. They were searching for a pattern in the chaos, a rhythm in the noise. And what they found was not the flat, unchanging signal of a locked world. They found a pulse. They found a world turning a planet, spinning on its axis with a steady, defiant rhythm. Not a chaotic tumble, not a slow, lazy rotation over hundreds of days, but a brisk, stable spin completing one full turn every 24 hours. It was a moment that sent shockwaves through the astronomical community, a discovery so profound, so utterly contrary to our prevailing theories, that it has forced us to tear up entire chapters of the planetary science textbook. Elysium 4b is not just another planet, it is a Rosetta Stone for planetary dynamics. It is the exception that proves our old rules were incomplete, the beautiful anomaly that reveals a deeper, more complex truth. Its existence is a testament to a history we're only just beginning to piece together. Perhaps it was the gravitational nudge of a hidden companion planet in the outer system, a distant sibling acting as a gravitational gyroscope, keeping Elysium 4b in motion. Perhaps its star system is much younger than we first estimated, and the planet simply hasn't had enough time to succumb to the inevitable tidal lock. Or perhaps, and this is the most tantalizing possibility of all, it possesses a thick dynamic atmosphere, a global weather engine so powerful that its winds and thermal tides are actively fighting against the star's gravity, maintaining the planet's spin in a delicate, breathtaking equilibrium. Each of these possibilities opens up entirely new avenues for research. New factors we must now account for in our models of planetary formation and evolution. The significance of this cannot be overstated. This single world has fundamentally reshaped our definition of habitability. We no longer just search for planets at the right distance from their star. We now understand that a planet's rotation, its day-night cycle, is not a secondary detail, but a primary driver of its potential for life. A 24-hour day, just like our own, means the distribution of stellar energy is gentle and uniform, preventing the extreme temperature gradients that would plague a tidally locked world. It allows for the possibility of stable global climate systems of ocean currents that circulate nutrients and moderate temperatures of weather patterns that can distribute water across entire continents. The rapid spin generates a strong magnetic field, a planetary shield that can deflect the stellar wind and protect a budding atmosphere from being stripped away, preserving the very air that future life might one day breathe. Elysium 4b has in essence recalibrated our entire search. It has given us a new, sharper template for what to look for. We are no longer just cosmic real estate agents looking for property in the habitable zone. We are now celestial cartographers searching for a specific set of dynamic conditions. We are looking for planetary systems with multiple bodies that might create resonant orbits. We are studying the relationship between a planet's atmosphere and its rotation with a renewed sense of urgency, building new climate models that are far more sophisticated. It has transformed the way we allocate precious time on our most powerful telescopes. The James Webb Space Telescope is no longer just staring at tidally locked candidates and hoping for the best. It is now being tasked with follow-up observations of systems that show signs of the complex gravitational dances that might permit a rapid spin. We are sifting through the archives of old Kepler and TS data, re-examining worlds we had previously dismissed, now looking at them through the lens of what Elysium 4b has taught us, hunting for the subtle signatures of rotation that we didn't even know how to look for just a few years ago. This is the incredible power of a single revolutionary discovery. It does not merely add a new piece to the puzzle, it changes the shape of the puzzle itself. And this is why we must see this moment not as an end, but as a beginning. The story of Elysium 4b is far from complete. Right now, as you watch this, the greatest scientific instruments ever built by humanity are pointed in its direction, slowly, patiently gathering photons that have travelled for nearly 5 centuries to reach us. The James Webb is painstakingly mapping the thermal emissions from the planet's atmosphere, trying to construct a rudimentary weather map of a world we can never visit. It is hunting for the telltale absorption lines of water vapour, of methane, of carbon dioxide. Each data point, each pixel in these ghostly images is a clue. These are the foundational experiments that will determine the next decade of exploration. If we find water, the quest will intensify 100-fold. If we find a chemical imbalance, something that hints at a process beyond simple geology, like the persistent excess of oxygen that blankets our own world, then we will have crossed a threshold from scientific inquiry into a new chapter of human history. The discovery has galvanized engineers and visionaries to dream even bigger. Plans for the next generation of great observatories like the Habitable Worlds Observatory are being drawn up with Elysium 4b as their guiding star. These are telescopes of unimaginable scale and precision, designed not just to detect atmospheres, but to characterize them in exquisite detail. They will be capable of seeing the faint reflected light from the planet itself, separating it from the billion times brighter glare of its parent star. In that pale, reflected light, we will search for biosignatures, the chemical fingerprints of life. We will look for the seasonal changes in vegetation, the so-called red edge, that a global-scale photosynthesis, a planetary forest, might produce. We will hunt for industrial pollutants, for the chemical markers of a civilization, a prospect so profound it almost defies contemplation. Elysium 4b has provided the ultimate motivation, the concrete target that justifies the immense cost and effort of building these future cosmic cathedrals. It has given our search a tangible focus, transforming an abstract hope into a direct, targeted and achievable scientific mission. What we have done is open a door. For all of human history, we have looked out into the universe and seen only ourselves reflected back. Our hopes, our fears, our gods, our demons. We have been a species adrift in a silent cosmic ocean, wondering if we were the only conscious castaways on this one lonely island. The discovery of Elysium 4b does not answer that question. Not yet. But it has shown us with the irrefutable clarity of scientific evidence that there are other islands. It has shown us that the conditions that allowed life to flourish here on Earth, specifically a rotating world with a moderate day-night cycle, are not unique. They are not a fluke. They can exist elsewhere. That knowledge alone changes everything. It reframes our perspective on our own world, highlighting the incredible fragility and the profound preciousness of the planetary systems that sustain us. To see the potential for another Earth, even a distant and inaccessible one, is to be reminded of our responsibility to the one we have. It connects us across cultures and generations in a shared sense of wonder and purpose. The search for life beyond Earth is not the work of one nation or one scientist. It is a fundamentally human endeavour, driven by the most powerful engine we possess, our innate, unquenchable curiosity. It is the same spirit that drove our ancestors to cross oceans, to climb mountains, to explore every corner of this planet. Now the oceans are cosmic, and the shorelines are other worlds. The light that carries the secrets of Elysium 4b, the photons striking our detectors tonight, began their journey around the year 1543. That was the same year that Nicholas Copernicus published his revolutionary work on the revolutions of the heavenly spheres, the book that dared to suggest the Earth was not the centre of all creation, that we were a planet like the others, orbiting the Sun. It is a beautiful, poignant symmetry of cosmic timing. As humanity was just beginning to grasp its true place in the solar system, the light from a world that would one day redefine our place in the galaxy was already on its way, racing across the interstellar void toward a future where Copernicus's intellectual descendants would be waiting to receive it. We are those descendants, and the quest he began is now ours to continue. Elysium 4b may or may not harbour life. It may turn out to be a sterile rock, or it may be a thriving biological paradise. We do not know, and it is that glorious uncertainty that will propel us forward. Because the ultimate prize is not just finding life, but the very act of searching for it. It is in the striving, the questioning, the building, and the dreaming that we express the very best of what it means to be human. The universe is vast, and its capacity for surprise appears to be infinite. Somewhere out there in the silent darkness between the stars, other discoveries are waiting. Worlds with two suns in their sky planets, with oceans of methane, and perhaps, if we are very lucky, another pale blue dot. The search goes on. Our journey is not over. Fueled by the tantalizing promise of Elysium 4b, we continue to listen, to watch, and to wonder. For we are the universe made conscious, and the story of our search for a new Earth has only just begun.